What you are looking at on your screen right now is something that I'm going to call the ugly list. Ugly, ugly, ugly. Remember, I told you we have to have a way to rank these leaving groups. We've talked about leaving groups. We've talked about being in a relationship with someone ugly and then cleaving that off and substituting that with a prettier group. It's all about superficial looks, folks. That's how molecules behave, and we're just going to have to accept that fact. Well, here is the ugly list. What you see over on the right-hand side is a column, and that particular column, if you look at it up at the very top, says leaving group, right? So the best leaving group of all, the best leaving group of all of them, is going to be iodine, I minus. That means that iodine is the ugliest out of all. You know, if you've ever watched Saturday Night Live, and if you've not had a chance to watch the Fingerling Sisters, then you need to type in on YouTube Fingerling Sisters on Saturday Night Live. Well, there's an iodine in that bunch. You'll know what I'm talking about when you see her. But there's an iodine there. Nobody wants iodine. Iodine's too ugly for anybody to have. So iodine will get scrapped to the curb, and it will get scrapped for anything that follows down below it. That is how this ranking system is ordered. So if you're in a bar and fluorine comes in, well, if you're currently in a relationship with iodine right now, that's going to be flipped with fluorine as lickety-split as it can, and ends one relationship and it forms a new one. If you're in a relationship with chlorine and an OH group comes in, well, that OH group is going to catch your eye. You're going to look at it and you're going to go, hey, OH, why don't me and you make tracks and leave old chlorine here behind? And that's what the molecules decide to do, just based on looks only. So sad. But down at the bottom, I'm not going to look at hydrogen. We typically don't see that. But if you look at this NH2 group, this NH2 group is the prettiest of them all. I mean, that's kind of like the fairy tale of Snow White. Mirror, mirror on the wall, who's the fairest of them all? Why, Amine, my dear. I mean, that's what this all boils down to. So that NH2 group, the amine group, is what I refer to as the Mr. or Mrs. America of the bunch. If the NH2 comes in, it is all over, folks. All over. NH2 is going to get what they want every single time. It's the prettiest one in the room. And all the molecules will swamp to that NH2 group to exchange their leaving group that they currently have. Now, we're assuming that they have a leaving group. We're assuming that they are in a relationship with a leaving group that they can just cleave off and say, go on, I'm done with you. Hey, NH2, why don't you come over here? I'll buy you a drink or two. So this ranking system, folks, is nothing that I want you to memorize. This chart, like I said before, is a chart that's given with every single test that I give out. And I would also advise you to have this chart available to you when you complete the online assignments as well. This chart is a very important chart for us to use. So don't memorize. There's a couple of groups on here that we know. There's a couple of groups on here that I can at least briefly mention. The NH2 group we know. We know how to name those amine groups. That's one of the reasons that we introduced them very early on. The C triple bond C, look at this. Does that ring a bell? I hope so. Because we saw this in the reactions of the alkynes, right? So we called this the acetylide ion. Acetylide is very pretty. Acetylide can also go in and pretty much replace anything that's above it, the way that this chart is organized. The OH group is the hydroxyl group. Otherwise, we would call this an alcohol group. That alcohol group is also very attractive to molecules. Very pretty. Not the prettiest, but one of the prettiest. And then we have things like the OCH3, which possibly could end up making an ether. We see some sulfide compounds. We see a C triple bond N, which is a nitrile compound. SH, which is a thiol group, not an alcohol group, but thiol group, THIOL. We see the OC double bond O. This is what we call an ester group. And then we also see fluorine and chlorine and bromine on there as well. Now, we kind of summarized that fluorine and chlorine and bromine were pretty ugly. They can easily be left behind and replaced with something else, and that's why we have the whole lecture based around the alkyl halides. And this is one of the reasons why. Most of the halides are at the top of this particular list, which means that they are the ugliest. Look, iodine, bromine, chlorine, and fluorine is not that far behind. There's a couple of things in between, but look at these. That carries no charge. Water carries no charge. So here I'm not even going to count those. So really only two other groups, and they're sulfur groups, that come in between the fluorine and the chlorine. So these are pretty ugly up here at the top. Molecules don't really want them. They're easily disposed of. Just get rid of them. So there's got to be a question of why this ranking system is based the way that it is. And I think the chart kind of gives that away a little bit. If you look in the middle column, you see that things are ranked in orders of pKa. pKa of HI is -10, and the pKa of ammonia, NH3, is going to be 36. What do we say about pKa values? We said that pKa values, and again, review of Module 1, we said that pKa values were really these values that tell us the pH of when the molecule loses a proton. So a pKa value of -10 means that if the pH level of that solution is greater than -10, then a molecule like HI will and iodine will leave on its own, yay, and carry a negative charge. In other words, what I'm saying is that I keep talking about the ugly chart, the ugly chart, the ugly chart. But is it really an ugly chart? It's what I use to get you to kind of think of it that way in the very beginning. And of course, it's not ugly. They don't really know what ugly is. But it's more like a Mr. Mrs. Independent chart. Because what we're saying here is that iodine feels very comfortable cleaving the acidic hydrogen that it has and going off on its own. And on its own means I with a full-blown negative. Iodine is very happy with that situation. It's very happy being single. And then if we take a look at ammonia, which is NH3, we have a pKa of 36. Well, that means that the pH of this solution has to be greater than 36, folks. Greater than 36 pH in order for ammonia to lose a hydrogen and become a NH2 minus. That means NH2 is not very good at being independent. It's clingy. It's needy. And if NH2 was out there, and if NH2 is on its own carrying that negative charge, it goes through some emotional stress. It can't deal with this being single for very long. It has to find a bond. It has to find a suitable carbon for it. And it doesn't care where it's coming from. It doesn't care. And to help it out in this search for a brand new man or woman, this NH2 group has to be okay with the idea of being pretty. That is where this ugliness term comes into play that I begin to use. It's all based on acidity. It's all based on pKa value. It's all based on their sizes and electronegativity. Because what we learned way back when is that the pKa values really are determinant upon a couple of things. Number one is the size of the group. What is that hydrogen attached to? So size is important. Electronegativity is also a factor. How greedy is it? Is it very electronegative? If so, it wants those electrons really, really bad. If it wants those electrons, it's more prone to kick off the hydrogen and take the electrons between the two atoms. So size and electronegativity plays a major, major role in this chart that I keep showing you up here. So keep this in your back pocket. You kind of understand the workings of this chart, the purpose of this chart, how this chart is ordered. And we're going to start using this chart in the reactions that they give us in this lecture. If you want a shorter chart, then here's an abbreviated one. And this one is actually flipped. So the ugly ones are down here toward the bottom, and then up here at the top, the amines are the pretty ones. Again, the Miss Americas. So here's an example, and we're going to use the ugly chart in order to figure out the answers to these questions. And folks, quite honestly, this should be how easy substitution is meant to be. So the example says, determine the product that would be formed between 2-bromobutane and the hydroxide ion, or 2-bromobutane and the hydroxide ion, S,3-chlorohexane and the hydroxide ion, and 3-iodopentane and the hydroxide ion yet again. So we need to work through these 4 examples, and hopefully you're going to look at this and say, is that all there is to it? And the answer is yeah. Again, no one said this had to be complicated, right? So let's start with our first example. The first example says 2-bromobutane, and we're going to react that with hydroxide, which is OH minus. And we want to know what happens here. So before we can figure out what the product is, we're going to have to draw 2-bromobutane. Did you pay attention back in lecture module number 3 when we started talking about alkanes and how to name them? It's coming back. I told you. So 2-bromobutane, 4. 1, 2, 3, and 4. On the second carbon, I have a bromo group. So on the second carbon, I have a bromo. Well, what do we know about bromo now? At this point with a substitution reaction, folks, we know this chart. And this chart says bromo is here, right there, and the hydroxide is way down here. So bromo is much uglier than the hydroxide. So if this carbon goes and sees hydroxide, folks, some cheating is going to happen, or maybe some substitution is going to happen. And what we end up with is a 4-carbon chain just like before. And instead of the bromo here, OH is going to go there. And bromine's okay. Bromine can go on, take care of himself. Not a big issue. Doesn't need to be in a relationship. Quite honestly, very happy being single. You've just done your first substitution reaction. That's all there is to it. Again, it's just really determining whether this goes forward as an SN2 reaction or an SN1 reaction, because there's going to be slight differences in how those substitution reactions go forward. So sometimes it's not going to change a product, and sometimes it does. So we just have to watch out for those when that time comes. But right now, we're just introducing things. That's it. That's all that we're doing. So 2-bromobutane reacts with hydroxide in order to give us butanol, but I've got to put a 2 in front of it because the 2, second carbon, has the OH. So 2-butanol, and the bromide on. That's all it takes, folks. That's it. That's a substitution reaction wrapped up into one nice little easy peasy example. Let's take a look at another one. R2-bromobutane reacts with OH. Okay, so here's the thing that they like for us to do here. They're telling us R. So what they want us to do, what they expect us to do, is to take this molecule like we've kind of drawn up here, and they want us to convert that over into something that's stereochemistry related. Well, that was lecture module number 6, right? Or 7. So all of this is also a review. So this is how we do it. We're going to start out drawing butane, just like before, 1, 2, 3, 4, and on the second carbon, we're going to put a bromo group. Now, it tells me specifically that I better have an R here. All right, well, we know this is not chiral, and we know that one's not chiral, and we know that this one's not chiral. We know that definition. We've done it in stereochemistry so many times. There's 3 hydrogens there, 2 hydrogens on that one, 3 hydrogens on that one. You can't have it. You have to have 4 different groups. Well, it just so happens that this carbon right here does have 4 different groups: a bromo, a methyl, an ethyl, and a hydrogen that's not drawn. It's understood to be there. So I need to make sure that I'm going to draw a representative diagram, and I can do it like this. If I want it, I'll just flip it around on you a little bit. Perfectly fine. There we go. That represents the R group. Well, hydrogen's there. I've got the freedom to draw the group. Hydrogen gets put into the back. So that way I've got 3 other groups that I need to kind of prioritize and rank. And I need to make sure that I go right-handed because that's the R rotation. So out of these 3, I've got a carbon, and a bromine. Bromine is going to have the highest priority because it's got the highest atomic number. Now I've got a tie between the carbon, and I move on to the next, and that's another carbon, and over here to the left, I run out. So CH2CH3, I'm going to put here. And then my CH3 group, I'm going to put there. This allows the rotation to go this way, and that is a clockwise rotation, and that clockwise rotation is the R stereochemical designation. All right, so there we go for that one, and I'm going to react that with OH, folks. What happens? Okay, well, the same thing's going to happen. My bromine is going to get substituted, and it's going to get substituted for the OH. But there's some things that I'm leaving off here. And one of the things that I'm leaving off is we're going to assume that this is an SN2 reaction. I'm just telling you that. We'll get to a point where we'll be able to pick it out ourselves, but right now we don't really know how to do that. So SN2 reaction is going to happen. SN2 means the carbon's a cheater. And a cheater means it sees both things at the same time. Well, when one goes out the front door, the other one has to come in through the back door. Remember that? And I told you in the world of stereochemistry, when SN2 is involved, this coming in from the back door approach flips our stereochemistry around. So that means what is R will now be forced to be an S because it's coming on the opposite side. We call this a Walden inversion. That's the appropriate term that we use for SN2 reactions. That is where R goes to S and back and forth. So this is what we do. I worry about stereochemistry last. I look at this molecule and I replicate the reagent. All right, so there's my bromo. Here's my CH2CH3. Here is going to be my CH3 group. And there's going to be the hydrogen. So I know that bromine's going to be kicked to the curb because it's so darn ugly nobody wants to look at it. And I know that OH is going to come on to that space. Just kind of what we did up above. It's the same molecule, right? In part A, they didn't want you to worry about stereochemistry. In part B, they did. They gave you the same molecule, they just slapped an R in front. So if I look at the way this molecule is oriented, and I begin to rank them, they're going to be ranked the same way, folks. We see a rotation that goes clockwise. So right now, this is the R form, and that's not what I want. The SN2 reaction is going to go through a backdoor approach. So therefore, it flips the stereochemistry. I need to make sure that I show that in the molecule at this stage. And the way that we do that, we pick two groups and we just flip them. That's all that we do. We just flip them. So I could, if I really want to leave the hydrogen in the backside, just take the ethyl group and take the methyl group and flip those two positions around. That's all you got to do. So OH now goes to the ethyl, which now goes to the methyl. That is a counterclockwise rotation. That leaves me with the S formation, which is what I need. And this is going to be S2-butanol. And there you go. That's how we do that SN2 reaction. Before I do the other two examples, I want to go over a little bit of mechanism work because I think that we lose some of that if we don't see it often. So 2-bromobutane, 1, 2, 3, 4. 2-bromo is going to go there. And here is the OH group that's there. And maybe we want to show the mechanism of this reaction. So this is how we do it. This bromo is going to be slightly negative and this carbon is slightly positive. I'm not going to leave those on there, but you need to understand that, right? This is a polar bond. There's unequal sharing of electrons. One end is slightly negative and one end is slightly positive. All right, so we know that. So I'm going to erase those. It jubbles up everything. We don't want to look at it. So this nucleophile, the negative hydroxide, very pretty. That hydroxide has walked into a bar. And that hydroxide maybe has its eyes sat on that carbon. And that carbon right now is in an awful relationship with nasty old bromine, and nobody wants that bromine. So that carbon's looking. It's actively looking, and it's okay because it's showing its partial positive to the OH group. I mean, that could get him arrested. He better be careful. So the OH group is going to come in, and it's going to attack that carbon. Notice what we had to do, though. We're on the opposite side of that carbon because this carbon is still involved in the bond with bromine. So when the OH comes in and makes this attachment to say, hey, you want to go out? I think we can make this work. Carbon's going to go, okay, yeah, but first I got to get rid of this nasty thing that I brought to the bar with me. So those electrons go off with bromine, and now we end up with the bromide ion, and we end up with a product, and that product is 1, 2, 3, 4 that now has this OH group on it. I drew it down just to kind of symbolize it came through the back door, folks. That's the only way that this would work. It's the only option that this carbon has. That bromine is on the other side of it. The OH and the bromine can't see each other right now. And the reason is because if they do, they're going to get into a fight. They're going to fight over that carbon. And that bromine, which is loaded down with electrons, and the OH group, which also has a negative charge, well, those negatives begin to repel each other, don't they? That's exactly what happens here. So that's why this cannot go forward at all. So the only option is for OH to go on the opposite side of the house, sneak through the back door, attach to carbon, and persuade carbon to ditch that old bromine because it's not doing anything for him like the OH can. All right? So this is what, again, we call the Walden inversion. Walden inversion is very important in the SN2 world. It's something that we always have to think about. Sometimes they don't really care about them because they just give me a molecule like this and they just say draw it and predict it. And other times they give me the R and they give me the S's. And whenever they do that, that is a very clear sign they want stereochemistry included in the problem. All right, now let's take a look at example C. Example C says S3-chlorohexane is going to react with the OH group. So we need to know what can we do, what kind of product can we get, and we also know stereochemistry is going to have to be involved here too. They give me an S out in front. So again, dead ringer. That's what I got to do. So 3-chlorohexane. All right, well, hexane's 6 carbons. 1, 2, 3, 4, 5, 6. There we go. 3, spot 3, we have a chloro group, and it's there. 3-chloro. But the problem here is that they give me the S. I wish they could just keep it simple and just say this reacts with OH. What happens? It's a very easy problem. But because they give me the S, they want me to show a little bit of the stereochemistry. So I've got to do this mess all over again. All right. So here's the carbon that is chiral. That carbon has a chlorine on it, which would be the highest atomic number. It also has a hydrogen on it that's not drawn. That's the lowest. It goes in the back. And now we have the ethyl group and we have the propyl group. Now this is S, which stands for sinister because left-handed people are evil, just like me. So left-handed means chlorine is at the top, and my next highest priority will have to go left-handed. Out of the two, that is my propyl group, my 3 carbons. And then I'll have an ethyl group that's left over here. So there is the S3-chlorohexane. Now I can put CH2 and CH3 if that's really what you want. That's okay. CH2, CH2, and CH3. That's fine too. Some people need to see it, and that's okay if you are. Not a problem. And now I'm going to react that with OH. Again, I want to show stereochemistry. But the actual reaction's pretty simple, folks, because the only thing I have to do here, chlorine is ugly, OH is pretty. So OH goes in and it switches for the chlorine that's already on the molecule. If you go back to the chart, you'll see chlorine up at the top with bromine and iodine, and then you'll see the OH toward the bottom, which means it's pretty. Again, that carbon's all about the looks. So OH is going to come in and take the place of chlorine. And we still want to show stereochemistry because that's how the problem was set up. I'm still going to put the hydrogen in the back. And folks, we have to understand that this also is an SN2. Again, I'm telling you that now, but later on we need to predict that for ourselves. And if this SN2 reaction happens, then that means Walden inversion is going to happen because that OH, just like up here at the top with that example, has to attack the backside of the carbon. So what was S in this case now has to end up being an R. And we need a R3 hexanol is what we need to end up with. Well, the easy way to do it, pick 2 of these groups. Well, we're going to keep OH on top. That's typically where I like to keep it. We're going to keep hydrogen in the back because that's typically where I like to keep that. And then the other 2 groups, we're just going to flip-flop around. So we'll put our ethyl group here, CH2, CH3, and we'll put our propyl group here, CH2, CH2, and CH3. Now OH goes to propyl, goes to ethyl. That goes in a clockwise direction, and that clockwise direction is an R group. So there we go. Stereochemistry right there and out. All right, so we've got one more example to do together, and this example is going to be 3 Ahodo pentane with hydroxide. Very easy one because, folks, it doesn't give me anything about stereochemistry here. That's great. Pentane, how many carbons? 5. 1, 2, 3, 4, 5. Ahodo on the third carbon. It's going to be here. Talk about ugly. Iodine is the ugliest of them all. So that carbon's going to be very happy to get rid of that iodine and replace it with something else and substitute it. And what does it substitute it with? It substitutes it with the OH group. There you go. That's all there is to substitution. Have a nice day, right? That's all there is to see, folks. 1, 2, 3, 4, 5. This is a pentanol, and at carbon number 3 is where my OH group is going to be located. There you go. If you wanted to show a mechanism, pretty easy. Take this OH, that's the nucleophile, attract it to the carbon, which is the electrophile, slightly positive. That carbon says, ooh, hubba hubba. And then it takes these electrons and it says, get out of here, iodine. You're too ugly. I don't want nothing to do with you no more. Go find somebody else to bother. And that iodine goes, okay, I'll take them. And then away it goes. But it finds out that it's perfectly okay with those electrons on its own. And it's going to take a little bit for it to find another partner in life. So sad. All right, so that's the story with substitution reactions. But we've made some assumptions here. You've not known it. I've known it. And what we're going to find out is that this is going to slowly blossom open, and we're going to start to see some exceptions. We're going to have to start determining SN1s and SN2s, which could change the products here slightly. Not major, but slightly if we're not careful. So that's the things that we're going to have to work through as we go throughout this lecture module. But folks, other than that, this is substitution at its heart. This is really all that we're doing. We're taking an ugly group, we're replacing it with a better group, and that is substitution. It's just, how does it happen mechanism-wise? What are the little bitty exceptions that we have to worry with or that we have to think about? And you're already seeing one of them. And that one of them is with Walden inversion. And that goes R to S and S to R only when SN2 is going to happen. All right, so come back to me. There's more to this than what I'm showing you now, and you're going to figure that out a little bit later on in the videos. So don't get too comfortable, but if you're okay with this kind of stuff, I think that you'll be okay with the rest of the lecture module.